Here is your 5 a day. And here are the answers. So today we're going to look at proof by mathematical induction. Now, the way it works is often likened to knocking dominoes over. So if you line up all of your dominoes, you push over the first one, all of the ones afterwards fall down. So mathematically, if we want to prove that something is true for all possible cases, for example, for all natural numbers, let's say, then we can't do it numerically because there are an infinite number of natural numbers and it would take us an infinite amount of time to test that it works for all of them. So what we do instead, or what we can do instead, is we can show that if one case is true and the next case is true, then it must be true for everything, for every case. So we start with the basis. We show that a statement can be proven to work for n equals 1, for example. Sometimes we might not start at n equals 1, but that's the most common. Then we assume that the statement is true for n equals k. Then we show that if the statement is true for n equals k, then it is also true for n equals k plus 1. That's a bit complicated to imagine at the moment, but it will become much clearer as I go through some examples. And then we conclude that we've shown that if the statement is true for one case, it must be true for the next, so it's true for all cases. So here are the 5 steps that you need to go through each time. Write these down so you can kind of check them off as you go through each of the proofs. Now there's a variety of different ways that we use mathematical induction. It's the same idea each time. It follows these same 5 steps each time. There's just different types of things we can use it to prove. So I'm going to go through a few of those with you now. Here's the first one. I'll give you a moment to read what it says. So my 0th step is define the proposition. My first step, show that it's true for n equals 1. So when n equals 1, my left-hand side here just goes up to 1. My right-hand side is 1 squared, which is 1. I have to show the substituting of the 1 into the left-hand side, substituting 1 into the right-hand side, show that they are equal, and say, so I know this is true. Okay, step 2. Assume that pk is true. So rewrite your proposition statement with k substituted in for n. Step 3. I'm going to calculate p of k plus 1 now. So substitute k plus 1 into the left-hand side of the proposition. So that's what I've done here. Don't worry about simplifying this for the moment when you write it out for the first time. Now this is exactly the same as this. So instead of having this whole big sum, I can replace it with k squared. So I can rewrite this as k squared plus this is just the same as this. Now I can expand the brackets and simplify. And I can factorise to get k plus 1 squared. K plus 1 squared, k squared. So I have shown that this is true for k plus 1. 4th step is the conclusion. You need to use these exact words every single time. We have proved that if p of k is true, then p of k plus 1 is true for k in the natural numbers. By the principle of mathematical induction, it follows that Pn is true for any natural number n. Pause the video now while you have a go at question 1. Okay, so we can use proof by induction to show that certain expressions are divisible by certain numbers. So let's start with our 0th step, define our proposition. First step, substitute in n equals 1. 7 to the power of 1 minus 4 equals 3, and it's important here, which is divisible by 3. If you don't want to write which is divisible by, what you could do instead is write which equals 3. I need to use a letter that I'm not going to use it. So let's say 3a for integer a. Next, second step. Assume that pk is true for k in the natural numbers. So we just rewrite our statement here with n equals k. And then here I've chosen m, so equals 3m for the integers m. Third step. Substitute in n equals k plus 1. So here I've just changed it to this. I can use my index laws to rewrite this as 7 times 7k minus 4. Now 7k minus 4, I'm sorry, I've decided to do it slightly differently. 7k, if I go back up to part 2, I can rearrange to get 3m plus 4. So I'm going to substitute that in. Now I can expand the brackets and simplify. I'm trying to find whether it's equal to 3 times an integer, so I factorise the 3 out, and I know that m is an integer, and so 7m plus 8 must be an integer. Therefore, 7 to the power of k plus 1 minus 4 is divisible by 3. Step 4, the conclusion, which you must always state. We have proved that if p of k is true, then p of k plus 1 is true for k in the natural numbers. By the principle of mathematical induction, it follows that Pn is true for any natural number n. Pause the video now while you have a go at question 2. Okay, here we're going to look at using proof by induction to show that an inequality is true. Note here that it's for all n greater than or equal to 3, n in the natural numbers, so we're not going to start at n equals 1. Let's start with defining our proposition. Now, we choose the smallest natural number that we can, which in this case is 3. So p of 3, 3 to the power of 3 is greater than 3 times 2 to the power of 3. Let's check. We need to evaluate those. 3 to the power of 3 is 27. 3 times 8 is 24. It is true that 27 is greater than 24, so P3 is true. P of 3 is true. Step 2, assume that it's true for n equals k. Make sure we reiterate that our k, just like our n, is greater than or equal to 3. Step 3, now this is going to work a little bit differently. It's a good idea here to, and this isn't part of your working, but to have a look at the statement that we're trying to end up with. So I'm going to start with my left-hand side, 3 to the power of k plus 1. That's equal to 3 times 3 to the power of k. I've just used index laws there. From my assumption in part 2, this must be greater than this. So the 3 has stayed in the same place. 3 to the power of k is greater than 3 times 2 to the power of k. Now we need to be slightly imaginative here. This statement here is going to be greater than this statement here because 3 times something is greater than 2 times something when it's positive. We know that these are all positive. So I can rewrite this second part, 2 times 2 to the power of k, as 2 to the power of k plus 1. And if you note, that's what I was after. So I have shown that 3 to the power of k plus 1 is greater than 3 times 2 to the power of k plus 1. As always, step 4, I need to state my conclusion. But we have proved that if p of k is true, then p of k plus 1 is true for k greater than or equal to 3. And really, I should also say here, k in the natural numbers. By the principle of mathematical induction, it follows that Pn is true for any natural number n greater than or equal to 3. Pause the video now while you have a go at question 3. Okay, next example, you can see here we've got a recurrence relation. So my 0th step, I seem to have lost my 0 here. For each natural number n, let Pn be the proposition that Tn, so this is what I'm trying to prove, Tn equals 10 to the power of n plus 1. Step 1, let's test it for n equals 1. So when I know that T1 here is 10 to the power of 1 plus 1. I'm told that T1 equals 11, so this is true. Step 2, assume that it's true for natural numbers k. Step 3, let's see what happens when n equals k plus 1. So in this statement that I'm trying to prove, t of k plus 1 equals 10 to the power of k plus 1 plus 1. Now, tk plus 1, let's look at this first part here, is 10 times tk minus 9. Tk, from my assumption at step 2, I can rewrite as 10 to the power of k plus 1. I can then expand my brackets and write 10 times 10 to the power of k as 10 to the power of k plus 1. I can simplify the 10 minus 9 here. And this was what I was aiming for. So tk plus 1 is equal to 10 to the power of k plus 1 plus 1. Finally, step 4, my conclusion. We have proved that if pk is true, then pk plus 1 is true for k and natural numbers. By the principle of mathematical induction, it follows that Pn is true for any natural number n. Have a go now at question 4. And here's a variety of other ones, questions 5 to 7 and 10. Have a go at these ones too. Thank you.